Our first speaker this evening is Dr. Jeffrey Short. Jeff left a long and distinguished career with NOAA and beyond. He was boots on the ground after the Exxon Valdez oil spill within days. And he's going to share with us some of the scientific legacy that he helped create and that we are continuing to build on decades later. So with that, I'll turn it over to Jeff.
Thank you, Danielle, and welcome to this event, and thanks for coming to hear me talk to you about the scientific legacy of the Exxon Valdez. So I especially also want to thank Danielle, Verna, and her colleagues for inviting me to speak to you tonight about the scientific legacy of the Exxon Valdez. It's been, what, 36 years now? Yikes. So many of you were too young to remember much of it, or some of you possibly weren't even born yet. So for me, though, it was the defining issue of my 30-year career with NOAA Fisheries. And as one of the very few chemists involved in this, I had a substantial role in the damage assessment all the way through for about 20 years. Before I start, though, I want to give a heartfelt shout out and thanks to all of the many hundreds of government, academic, and industry scientists, including the Prince William Sound RCAC, who worked so hard for so long to salvage some good out of what was otherwise an unmitigated disaster. So in the next about 20 minutes, I'm going to touch on why the Exxon Valdez was such a unique scientific opportunity to find out how large oil spills could affect marine life and ecosystems. And then I'll touch on the state of knowledge and assumptions that were widely held prior to the spill. And I'll summarize some of the most important discoveries that came out of it. I'll conclude with a brief comparison of the Deepwater Horizon, which I was also involved with pretty heavily, and that happened in the Gulf of Mexico in 2010. So the Exxon Valdez was a unique opportunity for four major reasons. First, it occurred at the very worst possible time. It was the beginning of oceanographic spring when countless migratory birds were converging on the Alaska's southern coast to reproduce. Marine mammals were giving birth to their young. Fish were fertilizing their eggs in the waters and shorelines, especially within the relatively protected waters of Prince William Sound, where the spill originated. Second, it found a productive and fully intact marine ecosystem where human disturbance was light or more usually absent. At 3,400 square miles of embayment and about less than 10,000 inhabitants, most of whom lived in Whittier, Cordova, and Valdez, the most common sight of humans in the rest of the Sound was the occasional commercial fishing boat, oil tankers, or ferries. That meant that there wasn't very much really in the way of confounding background contaminants or other human-caused stressors to confound the effects of the spill. Third, while most of the region was remote, it was still relatively accessible. Cordova had daily jet service to Seattle, and Whittier and Valdez were connected by roads to the North American road system, and that was invaluable for providing crucial logistical support. And finally, it occurred in a wealthy state and nation that could rapidly mobilize enormous resources to evaluate the effects of the spill. So those of us who were in the game before the spill happened recognized that it was an extraordinarily unique combination of events and scientific opportunity, and one that needed immediate action to take full advantage of. So here's four major assumptions that were current prior to the Exxon Valdez. The first one was that the most visible damage would be to organisms that occupy the sea surface, like seabirds and marine mammals. The second was that oil-contaminated shorelines were assumed to recover rapidly too, through a combination of physical dispersion and natural biodegradation of the oil. It was also assumed that mobile organisms, such as fish and marine mammals, would sense and avoid oil if at all possible, thereby mitigating toxic effects. And finally, toxicity studies prior to the Exxon Valdez seemed to indicate that oil wasn't really actually very toxic to marine life, in large part because oil and water don't mix very well. The Exxon Valdez showed that none of these assumptions was entirely correct, and some of them were outright wrong. So for some background, bring back memories for some of you. The spill began on Good Friday, March 24th, 1989, when the tanker hit Bligh Reef, spilling nearly 11 million gallons of crude oil into Prince William Sound. Initially calm weather allowed the slick to expand at a rate of about a quarter of a football field per second, straight for 2.5 days. That made it almost impossible to contain. Third, the initial response efforts included 4 dispersing tests, one of which was partially successful, and a small in situ burn experiment. But by Sunday, high winds from a winter storm arrived, and that terminated all of those efforts and drove the slick southwest and into the Gulf of Alaska. Continued southwest, eventually oiling about 700 miles of shoreline, extending past the southeast end of Shelikof Strait, and took about 55 days to get there. About half the spill volume beached, 20% evaporated, and 20% dispersed into the water column. Most of the remainder was skimmed. So skimming mechanical recovery got about 10 or less percent of the oil that was spilled initially. So as expected, the surface oil killed wildlife in droves. Estimates ranging between 100,000 and 690,000 seabirds were killed, along with 2,000 sea otters, 300 harbor seals, and some killer whales and sea lions were also probably killed, but those estimates are not very precise. So nearly everything died on heavily oiled shorelines, such as this one here, from physical smothering after wind-driven oil slicks piled up on them. These effects were assumed to be limited to the upper reaches of the tidal excursion, where dispersion from wave action was less effective and less frequent, resulting in a bathtub ring along these shorelines, which you can see here. This is a typical example of a bathtub ring. This is a pretty heavy oil slick, and there's the bathtub ring again. But in reality, oil could accumulate at any tidal level, depending on the tidal stage when the oil initially arrived. As the beach dehydrated on an outgoing tide, oil seeped into the underlying sediments, and it's not hard to imagine that, given if a beach started with this much oil on the top. Once there, capillary forces trapped the oil when the tides came back in again, and that set the stage for long-term exposures to shoreline-dependent wildlife. Studies conducted over 12 years after the spill showed that around 100 tons of oil still remained on beaches within Prince William Sound. Surface oil was the most common in the upper intertidal, but subsurface oil was distributed throughout the tidal excursion, and it occurred most frequently at the mid-tide level here. This is the distribution of subsurface oil on a typical beach in Prince William Sound. Consequently, surface oil was not a very reliable indicator of where you could find subsurface oil. The reason that the subsurface oil was so widespread and persistent was because of the availability of oxygen. Subsurface oil usually was found several inches below the beach surface, and this is a typical example of that, and there's the boundary right there. This is a heavily oiled subsurfacely oiled beach, and it's oiled up to that boundary, and above that boundary, which is quite sharp, the sediments looked all clean. So why is that? And the answer was oxygen. The level of the beach that was above there was well irrigated by tidal flushing, but the beach that was below there had stagnant flow of water, and that prevented biodegradation from occurring. And that set the stage for not only the long-term persistence of the oil, but this oil, this is like 12 years later, and it's still flowing. It hadn't weathered very much at all. So that created these long-term pockets that could continue to contaminate wildlife and also people that dug up beach sediments in search of food. This caused persistent exposures to sea otters, waterfowl, and wildlife over a decade, and seriously impaired access to an important source of subsistence foods for Alaska natives. These discoveries were entirely unexpected prior to the Exxon Valdez. So another surprise was evidence that fish and marine mammals actually wouldn't necessarily avoid oil. Field studies showed that visible oil was in the digestive tracts of juvenile fish, and lab studies confirmed that these fish will willingly consume oiled food. When they do, it slows their growth rate. This has effects on the population because vulnerability to predation is a very strong function of size. So even slightly reduced growth rates could reduce survival substantially. For wild pink salmon in Prince William Sound, it was estimated that this effect caused a 28% reduction in the return of viable adults to spawn. Also, oil in intestinal tracts of sea otters and other marine mammals indicated ingestion, although this may have been from their attempts to get it off their pelage. But in any case, photos of killer whales and marine mammals near or within oil slicks showed that they either couldn't detect the oil in time to avoid it or didn't find the oil sufficiently noxious. One of the most surprising results was the discovery that oil is much more toxic to fish when they're exposed as embryos. Inspired by field studies that showed survival of salmon eggs in streams that had been oiled was lower than elsewhere, a series of mesocosm experiments were conducted to see if oil could affect the embryos at very low exposure levels. Pink salmon eggs were reared in a series of different vertical plastic tubes, and it contained oiled gravel at various levels of contamination. When the pink salmon emerged from the gravels in the spring, they had increased mortalities and abnormalities that were directly related to the amount of oil loading on the gravel. Then the survivors were marked with a coated wire tag, microscopic almost, that got injected into their snouts, and they were released into the North Pacific Ocean to complete their life cycle. Because they're pink salmon, they all come back to the same place at the same time, which is real handy. And that allowed us to recover the tags and figure out proportional survival based on how much of a dose they were exposed to as embryos. The results were stunning. Exposure to 18 parts per billion is what that equates to of PAH, the most toxic component of oil, resulted in a 50% survival to maturity. We repeated this experiment twice, almost 3 times, and got the same result each time. This was 100 times more toxic than any of the previous Exxon Valdez toxicity studies had indicated. Subsequent research showed that embryonic exposure impaired development of the heart and circulatory systems, which led to a host of abnormalities. For example, these fish here, if you blow that up, they're sick puppies. These results made embryo toxicity effects a major focus of subsequent oil spills. Moreover, they led to an explanation for why heart attacks increase during urban air pollution events. The same chemicals are in urban air pollution, and they impair heart function in humans, leading to heart attacks. Effects on intertidal biota were extensively studied, and I can only summarize the highlights here. Mussels form dense beds in more protected and shallow gradient beaches, and these beds sheltered oil that penetrated beneath them, so they became longer-term reserves. This provided a continuing source that contaminated the mussels and created an exposure pathway for oil to be ingested by animals that consume them, including birds, sea otters, starfish, and many other species. Oiling and shoreline cleanup also killed a lot of seaweed, especially fucus, which is this stuff here. They cover a lot of the mid-intertidal and provide shelter for mussels and barnacles. Their loss, along with losses of predatory snails, led to replacement of the resident barnacles with opportunistic species. This was one of the first clear demonstrations of an indirect community effect on an oil spill, as indicated by this pretty complicated wiring network of how the intertidal network ecosystem reacted. This was in our science article. It was probably one of the most heavily cited articles of an oil spill on the planet. So, in 1993, crashing populations of pink salmon and herring in Prince William Sound suggested further community effects. These crashes hit the fishing industry really hard and resulted in demands that the trustee council direct their efforts at finding out what caused them. The fishing community emphasized their concerns by blockading the Valdez oil terminal for 4 days with their boats, interrupting the about 25% of the United States oil supply. The trustee council immediately got the message and recognized the need to understand the drivers of natural variation of salmon and herring recruitment. And these provided critical context for evaluating any lingering effects that may have been caused by the oil exposures. So consequently, the council launched 3 multi-year integrated ecosystem studies in 1994. 2 of these, the Sound Ecosystem Assessment and the Alaska Predator Ecosystem Experiment, focused primarily on studies to better understand how natural factors affect pink salmon and herring survival and the dependence of seabirds on forage fish. The third, the Nearshore Vertebrate Predator Program, was aimed at evaluating the effects of oil, life history, and climate on marine mammals and seabirds. Among many other things, the NVP studies documented the long recovery time of species that remained chronically exposed. So today, most of Prince William Sound is recovered from the spill, despite lingering pockets of oil that will probably persist for decades, and the lack of recovery of herring, the AT1 pod of killer whales, and pigeon guillemots, which haven't recovered apparently because of a shift in the availability of their forage fish prey. So turning now to the Deepwater Horizon, the discoveries from the Exxon Valdez motivated many of the damage assessment studies of that. At over 200 million gallons, the Deepwater Horizon discharged almost 20 times as much oil into the Gulf of Mexico as the Exxon Valdez spilled into the Prince William Sound, and was the biggest marine oil spill in history. It was a deep sea blowout, so the oil had to rise nearly a mile through the water column to the surface. So many of the damage assessment studies were focused on what happened to the oil before it got there and what it affected. After the oil reached the surface, much of it was driven shoreward, oiling several hundred miles along the northern Gulf of Mexico. As expected, the oil caused mass mortalities of animals on the sea surface, killing nearly a million seabirds, 100,000 or so sea turtles, and thousands of marine mammals. Marine mammals were found to be especially sensitive to the inhalation of toxic vapors from the oil slicks, often leading to lung diseases, something not anticipated from the Exxon Valdez. Toxic effects of oil on cardiovascular development and function in fish were extensively investigated in the Deepwater Horizon. These studies found toxic effects on embryonic through adult life stages of fishes that were up to 1,000 times more toxic than acute toxicity thresholds before the Exxon Valdez, confirming and extending the findings from the Exxon Valdez. Shoreline oiling was particularly damaging to coastal marshes, most of which were located in Louisiana. Oil accelerated marsh erosion, already a serious problem before the Deepwater Horizon. Among other things, these losses removed nesting and rearing habitat for a multitude of fish, birds, marine mammals, and other wildlife. Surprisingly, studies from the Deepwater Horizon also found that insects and spiders were very sensitive to exposure to oil pollution, and their losses deprived the birds that feed on them of an important source of nutrition. Another surprising study found that marine snow, which is basically congealed gelatinous material from dead jellyfish and other primitive sea life, can act as a pump to transport oil from surface waters to the seafloor, revealing a new contamination pathway. The Deepwater Horizon also had serious effects on ecological communities. As with the Exxon Valdez, shoreline communities were strongly affected by the oiling, and some of the damage was irreversible. But one of the most surprising effects on the nearshore ecological community involved the consequences of the mass seabird mortalities. Most of the million or so seabirds that were killed by direct contact with oil fed on juvenile forage fish, including juvenile Gulf menhaden, which support the second largest fin fisheries in the United States, just behind the Alaska pollock fishery. The abrupt losses of all these seabirds in the spring of 2010 removed an important source of predation pressure, resulting in record-breaking survival of forage fish. So many survived that these populations overgrazed their food supply, leading to near starvation in the most heavily oiled coastal regions. These effects persisted for 2 years through 2012, when recovery of seabirds and other species restored control over forage fish populations. So circling back to the Exxon Valdez, this same effect may have contributed to the 1993 herring crash in Prince William Sound. The mass mortalities of seabirds at that event would have lowered predation pressure on juvenile herring, which were already at unusually high populations in 1989. This release may have led to starvation conditions for herring, making them vulnerable to the diseases that have suppressed their recovery ever since. So in closing, the Exxon Valdez was by far the biggest contamination event in Prince William Sound ever, bigger than the combined total of all prior human interferences in the Sound that have ever occurred, at least in terms of shoreline contamination. Viewed as a gigantic natural experiment, the Exxon Valdez remains one of the most intensively studied spills in history and led to a much deeper understanding of how oil spills can affect plants, animals, ecosystems, and people. I thank you for your attention, and I look forward to your questions.
I know it's a tough one to answer with the chaos we are in with our present administration and the fairly recent past of the same. But it seems like both your work with the Exxon Valdez as well as Deepwater Horizon show that the contamination level that's a problem is in the parts per billion, and our Clean Water Act, if I'm right, is still stuck in the parts per million. Is that right?
Not exactly.
No. Okay. Well, good. Then that's the question I'm asking.
I'm not sure what the current status of regulation is, but for a while, the results of our study, initial study with pink salmon, resulted in a lowering of the discharge threshold within the state of Alaska ADEC regulations.
Great.
I think there was an attempt, and maybe it was successful, to back away from that over the last few years, but I'm not sure.
Thank you, Jeff.
Mm-hmm.
I'm not quite sure how to phrase this question, but a good friend of mine was a researcher from UW during the oil spill, and he kept saying, we just know nothing about Prince William Sound. We are starting from ground zero to even understand what was here before, accepting anecdotal information from commercial fishermen and indigenous people living in the area. So my question is, are places, to your knowledge, has the Exxon Valdez spurred any pristine places in the world, researchers to go and see what they have in those special areas that maybe there is industrial potential, so they have some baseline data? If something were to happen, they're not starting at ground zero. I don't know if does that make sense?
It does.
Okay, thank you.
And I'll give you a two-part answer. To directly answer your question, there are lots of places where people are doing exactly that, in part motivated by the Exxon Valdez, but in part not. The second part is your colleague's conclusion was actually misinformed. During the 1970s, and actually this is the program that got me to Alaska, when was contemplated opening the Trans-Alaska Pipeline, the federal government launched an enormous program to better understand what was here in marine life. It was the Outer Continental Shelf Environmental Assessment Program, and it was, if I recall right, $50,1972. So it was not chump change. And it led to an enormous literature and a huge updating of, right, before that, you were right, there was hardly anything. But that kind of set the baseline. And then chemically, our laboratory at Ock Bay immediately recognized with the opening of the pipeline that it'd be a real good idea to document the contamination profile of Prince William Sound prior to anything untoward happening. So we had a beach sampling program for sediments and mussels that occurred in, I think it's like 76 through 78 or so. And then when the spill happened, it was early Friday morning. By Saturday afternoon, we had a team on a plane going up to Prince William Sound to resample all those beaches before they got hit. And that didn't get a lot of press, but we made heavily use of it scientifically.
Yes, so the KSMSC conference room asked what kind of experiments was Exxon doing to get their toxicity results?
Well, the toxicity results that I referred to prior to the Exxon Valdez were not, some of them were done by scientists that worked for Exxon subsequently, but everybody was doing pretty primitive experiments. They were acute 96-hour toxicity experiments to see what concentration would kill half of the exposed animals within 4 days. After we published our first papers on embryo toxicity, Exxon researchers published studies that attempted to replicate those results and were unable to find the same results that we did. But we felt that that was because of a number of procedural errors.
Thank you. Mike Donnellan asked, how do you think the scientific lessons learned from EVOS and Deepwater would apply to spill response and evaluation of potential environmental impacts of a major crude spill in the Beaufort Sea?
Yikes. Well, there is, I was really fortunate to be on the panel of the latest Oil in the Sea 4 book that is a summary of everything that's pretty much known about oil pollution, produced by the National Academy of Sciences, and it just came out a couple of years ago. And those questions were addressed in that volume. But the bottom line, I guess, conclusion that I would take from that, because I wrote much of that, is that if there's a spill in the Beaufort Sea, you have so little logistical support, and the weather is so adverse that you would be lucky to really do much of anything at all. Thank you. Thank you so much.
Thank you, Jeff.